In this video, you'll learn about how you can remove particulates or pollutants by filtrations. So filtration is a physical filtrations where the pollutants is like, think of like a packed media like a sand particularly, and when the contaminated water moves from the top from the to the bottom, small pollutants like this will stick on the adjudged media or stick to the media so that can be filtered out. So these physical filtrations can be modeled so you can predict how much pollutants get removed or particulate matter. So when you say filtration, there are two types of filtration. One is called physical filtrations or straining, which is basically pollutants or the particles can be removed just because they are bigger than the size of the pores for which it's moving. So filtrations, straining is same thing as strain in the kitchen. The second time is this is the case where the particle size is greater than pore size. So this is particles. Simply the particles are bigger enough so that it gets stuck on the top. It cannot pass through the pore. And physiochemical filtration can occur when the particles are even the small particles cannot pass through the pore because even the pores are much bigger. The reason is small particles can be intercepted or stick to the or adsorb or settle on the pore size. So here is basically, think of this. You have media and you have this small pore and the small particle cannot move through it. But in this case, physical filtration is even your particle gap is much bigger, this small particle can settle or adsorbed or that intercepted directly in the movements and that can be removed. So this is called physiochemical filtration. It depends on all the different factors. So first thing is trending or physical filtrations. That it depends on the relative size of the particles compared to the size of the filter media. So that's why you can write, now this is the rate at which the amount of particles removed, which is basically density of particles times the pollutants they are removed, is basically the straining or the how much uh, the rate at which this thing straining can occurs. And that depends on the relative size of the particles and relative size of the filter media. So this is the size of particles, and this is the D50 or the 50%, the size of the particles that 50%, the size which is more than 50% of the particles. So that's the D50 means, basically the size, if you have a size distribution of the filter media, so this is basically filter media properties or the median size of the filter media. So that means if you know all these factors, the concentration of particles, ball density, everything, you'll be able to calculate how much is removed. And so there are certain numbers are given, this constant, if you put this constant, you'll be able to predict how quickly particles are removed. And so this is the journal articles you can refer to when you have to calculate this removal by straining. And this is pretty much relevant for large sediment particles, which are very rarely moved further from the sites. What you are really concerned about the very suspended particle, which are very small. For those, straining is not a big factor because they stay suspended, they mostly pass through the pores. So for them, the way that can work is basically physiochemical filtrations. So now, one of the factors to remember is when you have large size particles, they are removed on the top surface because of straining, they can clog the system because they can create a clogging or clogged cake layer. And so that clogging depth depends on many factors. It depends on the depth of filter media. If you have a larger filter media, so the depth you can clog on the top surface, but it leave behind still large media, large section of depth is unaffected. So that means just by increasing the depth of filter media, you'll be able to decrease the extent of clogging. Increase the particle size of filter media. So the case here is that if you put larger size particles, the clogging rate will be a lot slower. That means you'll still have high conductivity. And you can also remove the cake layer, which is basically the layer of sediments that deposit in the surface. If you just remove them, that will also restore the capacity of media to infiltrate water. You can also add vegetations. If you have plants, it turns out the plants has roots, and these roots will decay over time, and that will create preferential flow for water to move through it. So just by having these kind of factors, you will be decrease the extent of clogging. Again, just make the media filter much deeper, increase the particle size, add just more sand, scrape the any deposited sediments, and add plants. You can increase the infiltration capacity of your detention basin or infrastructures. Now, if you want to calculate removal of particles by physiochemical filtration, so this then you can calculate based on this. So basically, this R is equal to 1 minus N. N is the concentration of particles in the effluents, and N0 is the concentration of particle in the influents. So this is influence in, and this is out on particle concentrations. R is basically how much particles is removed. It turned out this removal fraction, or the percentage of particles removed or remain in the effluent, depends on this factor. That factor means L is the depth of media. So this is the L. L is the depth of media, and lambda is basically a filtration coefficient, and that filtration coefficient is a factor of many, is depends on many factors, which is one is sticking factor, which is alpha, and collision efficiency, and porosity, and suspended particle diameter. So this filtration coefficient is can be predicted based on this. So let's think of what those are. Alpha is the fraction of colloid particles stick to the grain. So think of this, the small particles when they move through the system, there is before for it to be removed, it has to collide with the surface. And so how likely they'll collide with the surface is called collision. And just because they are colliding doesn't mean that they're going to stick. They can collide and then come out, or they can collide and stick. If it's sticking, that's what's removed. That's why the alpha is basically the percentage of collided particles sticking to the system. So that's called a sticking factor. It depends on the porosity of the media, because this porosity is basically determined by this gap. So if the gap is if the gap is small, then you are more likely to have collisions and interactions. So that's why it depends on porosity. And also it depends on suspended particle diameter, because the larger the diameter, more likely they will interact or intersect. So if you think of all these factors, if you know all these factors, you can calculate lambda and you can predict how much particles is going to be removed. So that means all you have to do is calculate alpha and attachment coefficient, because you know the porosity based on how you pack the column. You know the particle size of the particles that need to be removed, or suspended particles, and you can assume the alpha attachment coefficient or sticking factors based on the properties. So now that leave behind, the only thing that you don't know is collision efficiency, and that collision efficiency can be calculated based on different processes. It turns out the collision can occur in one of the three processes. One is could be sedimentations or just settling. The particle can just settle on the filter media particle or collector, so that's called sedimentations. Another is they can diffuse and stick to the surface, or they can be just intercepted when the water is moving adjacent to the particles. So this combination of three processes will determine how likely they will collide, because collision can occur one of the three methods. So these are the equations that determines uh, those collision based on each of the process. So here is the intersection. This is basically settling. That's gravity settling that we just calculated a few minutes ago, and this is basically based on diffusions, and diffusion related to temperature. So that's why you can see that um, K put Boltzmann constants and temperature factor here. Everything else you kind of know. Interception is a relative functions of the size of the particles and the size of the filter media. If you are large particle, they are more likely to be intercepted. So all these factors, if you know, you can calculate collision efficiency, and you'll be able to calculate how much particles is going to be removed. So, well, now that you know the theory, how to design this? Well, first thing is if you see removal depends on the length of the filter media. So that means the first thing you could do is you can increase the length. If you increase the length, you will remove a lot more particles. Physically, how that is possible? Because if you have larger length, you have more chance of collisions to occur, more chance of the particles to stick to the one of the media. And then increase attachment sticking factor. Sticking factor is related to how quickly they can bind things, how can they can stick. So that is based on the affinity of the particulates towards the filter media. So that's based on the filter media type. If you make the filter media more attracted towards the particles, they have a significant attractive force, then you can change that. You can decrease the porosity by just making the size smaller. So if you put instead of sand, if you mix with some kind of soil or other materials, the relative porosity is going to decrease. So that means you can increase more removal. That's why if you have just sand filter and mix with some kind of amendment with smaller particles, they will remove a lot more fine particles. But in this case, the flow rate will decrease. Increase collision efficiency by decreasing diameter of particles, which you can do. But diameter filter media, again, you can make it smaller. You can slow down the water. By just decreasing the size of the filter media, the hydraulic conductivity also will decrease, and that will also make the velocity of water passing through the media is going to decrease. If the velocity decreases, that's more likely to stick. So now I encourage you to check the example in the book, which where you can use this informations to predict the removal in those sand filter. So the question here is the estimates the filtration removal efficiency for 10 micron particles with specific gravity of 2, that means it's twice as heavy as water, through a 0.5 meter depth sand filter during a 16 inch per hour in preparations. So the what is given is the length. Length is given 0.5 meters. That's the media depth, um, 0.5 meters, and then you have water is flowing at 16 inch per hour. So that's basically the flow rates. And then your size of the particles is given, and size of D10 sand, the smallest size of particle D10, or the particle size, that's a D10 of sand is given 0.8 meter, because the smallest particle that determines the removal rate. D10 is 10% passing. That what that means is only 10% of the sand is smaller than 0.8 millimeters. And the porosity is given is 0.4, and the size of the particles is given 10 micrometers, and the particle attachment efficiency alpha is 0.05. What that means, only 5% of the collision resulted in attachment. Temperature is 15 degrees Celsius. So all these variables are given. So that means you just have to first calculate. If you think of a filter removal efficiency, that's basically uh, removal efficiency n minus n0 uh, is that's the removal n by n0 is if you calculate n by n0, which is e to the power minus um, lambda and L. So now your goal is to calculate lambda, and lambda is basically here, these variables. And so that means alpha is given, the porosity is given, size of the particle is given. The only thing is not given is collision efficiency. So that collision efficiency, you know this from these equations, you can predict those variables based on all the parameters. So this is where it is given. So if you calculate collision efficiency for all these different factors, you'll get the number is this. And then you predict that value. There you can be able to calculate n by 0, g to the power, all those variables. So then you can calculate that this number is very small. What that means is your effluent concentration is very, very small, 11 order magnitudes uh, lower than the influent concentration. So that means now 100% particles will be removed. With that, you'll learn how to use filtrations to calculate how much particulates you can remove.